And now for something that you might recall from Calculus 3. I can tell you really enjoyed Calculus 3. Anyway, if you remember in Calculus 3, something called the total differential of a function f of x, y, actually I should say f of x, y equals c, but that's alright, at a point x sub 0, y sub 0 was defined as df, the total differential, equals the partial derivative of f of x, y evaluated at the point x sub 0, y sub 0, and by the way, I should have said partial derivative with respect to x evaluated at the point x sub 0, y sub 0 dx, plus the partial derivative of f of x, y evaluated, with respect to y evaluated at x0, y0 dy, where these are the partial derivatives that I had already noted at that indicated point. So geometrically, the total differential gives the instantaneous change in, I could say height of the tangent plane, but we could just say height of the surface above the xy plane, z equals f of xy at the point x sub 0, y sub 0. So it's the instantaneous rate of change of the surface at that point. And so that was called the total differential, and that is connected up with this thing called the exact differential, because an exact differential equation is one that corresponds to a total differential of some function f of xy, some function of two variables. F of xy equals some constant like that. So it may be defined like that.
Don't get technical with me.
Well, I'm sorry, I've got to get technical. So, alright, let's go look at this from a viewpoint. What is an exact differential? An expression of the form m of xy times dx plus n of xy dy is an exact differential if it corresponds to a total differential of some function that looks like this. Note that this corresponds to the partial derivative with respect to x of xy, and this corresponds to the partial derivative of f with respect to y at xy. So, take that exact differential and set it equal to 0, and we have an exact differential equation. Alright, so that's not so bad. So, here's an example of one of these. Look, x y squared dx plus x squared y dy is an exact equation since it's the total differential of f of xy equals 1/2 x squared y squared set to 0. See, take the derivative of this with respect to x, you get xy squared. See, xy squared dx. Take the derivative of this with respect to y, you get x squared y. See, x squared y dy, and set that to 0, and we've got an exact differential equation. So, the natural question is, how can you tell if we have an exact differential equation? That's the $64,000 question. So I suppose there must be some way, and the answer is yes. There is a criteria for determining if we have an exact differential equation. If m and n are continuous and have continuous first partial derivatives, from now on I might just say if m and n behave nicely in some region R, then m x of y dx plus n x of y dy is an exact differential, set it equal to 0, this is an exact differential equation, if the partial of m with respect to y equals the partial of n with respect to x. Now what that is saying, and I'll again ask you to bring back some of your Calculus 3 memory. And that would be that when you take the derivative of f with respect to x and then y, or if you take the derivative of this function f with respect to y and then take the derivative of that with respect to x, that they're equal to each other. And so in other words, we're saying the partial of this one with respect to y should be equal to the partial of this one with respect to x, because nicely behaved functions act that way. So here's the technique. Given that this is a differential equation, and if we want to know if it's exact, of course we do the check, that's this check, and see if it's exact, and if it is, so we note that the derivative of the function with respect to x is this m of xy. So then we integrate it. We integrate it, and f of xy therefore would be the integral of this with respect to x plus g of y, where g of y, which could be 0 or could be a constant or could be a function of y. Now, you see why it could be any function of y, because if you took the derivative with respect to x of some function of y, you'll always get 0. And don't forget the partial of our function f that we think we have the total differential of is n of xy, so therefore if we integrate that with respect to y and then add some constant which could be any function of x, including a number or 0, but we integrate this one with respect to y, then those two things have to be equal to each other. In other words, f of xy would have to be this, and it would also have to be this. And so we should be able to work out with constants to find the actual solution, f of xy equals 0. That's our function that we're finding the total differential of. Actually, to tell you the truth, I guess it would be f of xy equals c, and then an initial condition would allow us to find that constant c.